Hi guys and welcome to another Maths Guru video. My name is Darren, otherwise known as MaffsGuru, and it is really good to see you. Thank you very much for joining. This video is on area. Oh yes, the excitement doesn't start. Well, it does really. Now, if you haven't already done so, do me a favor. Can you head over to YouTube and subscribe to my channel? There is MaffsGuru.com, where all of these videos are searchable by textbook. They have downloadable notes. I have exam questions and all sorts of stuff there waiting for you to hopefully make you much better at maths. My job is to make maths easy and hopefully with a little bit of humour as well. So let's get going. Learning objectives. By the end of this lesson, I am looking for you to be able to convert units of area and find area of two-dimensional shapes. Now, if you're already stopping, don't stop. I know you've done this probably in years 5 and 6 and 7 and 8 and 9 and 15. There isn't a year 15. But the point of it is, it gets harder. The general ideas of area, not a problem. Basic shapes, easy peasy lemon squeezy. But we're about to get a little bit more complicated, and converting units of area is a really funky and really important part of the course. Now, obviously, the great thing about maths is what I'm saying is it has content that builds on it. So in a previous video, I looked at perimeter of sectors and arc lengths and all that type of stuff. In the first video, we looked at, the idea of finding perimeters and lengths. Yeah, it doesn't sound tough, but some of those questions got really funky. And I'm promising you now, some of this stuff is going to get really funky, and it's going to test your understanding. So, converting units of area. Here is a recap about converting units of area. We know that lengths, generally speaking, are given in terms of kilometers, meters, centimeters, and millimeters. Okay? So it's useful for us to be able to convert between each of those things. Right, I'm going to say, let's imagine we have a box that is 1 meter by 1 meter. And I now want to find the area of that. Well, we know what the area is. It's that times that, which gives me 1. So I now know for that, it is 1 square meter. That's the area. Now, again, we need to be careful. We have units of meters and floaty 2 for area. And the number of people who sadly miss out this type of stuff is sadly a lot. All right, so I'm now going to take my meters and convert it to centimeters. Now, sadly, a lot of people say, well, I know there's 100 centimeters in a meter, so I'm just going to times that by 100 and get the wrong answer completely, which is a shame. Now, believe it or not, it's not wholly incorrect, the ideas that they're having. I'm going to change this 1 meter into 100 centimeters. So what I've done is I've multiplied that side length by 100, yeah, because there's 100 centimeters in a meter. But I now have to convert this 1 meter into centimeters. And so that becomes 100 centimeters too, which is also times by 100. So what's actually happened is I've made my shape 100 times bigger that way and 100 times bigger that way. Hold on a moment, area has 2 dimensions. 100 bigger that way, 100 bigger that way. So actually, if I multiply this by 100 and by 100 again, that's going to give me the conversion between meter squared into centimeter squared, because I've taken that 100 bigger that way and 100 bigger that way. Now, we've got lots of ways we can write this in maths. We could write it as 100 times 100, but we can also say that that's 1 square meter times 100 squared. That floaty 2 means multiply it by itself. And then taking that and doing it gives us 1 and 4 zeros centimeters squared. So 1 square meter is actually 10,000 centimeters squared. And if we look at the diagram I've given you here, and this is an opportunity for you to take it and put it in a summary book if you're allowed to, and it will help you do these calculations. Well, I happen to work it out from first principles here. So let's just check. What were we doing? We were going from meter squared to centimeter squared, and lo and behold, it says times by 100 squared. Wow! Love this stuff. Let's just do one more from centimeter squared to meter squared. So again, I'm going to talk about the idea that this is 1 centimeter by 1 centimeter. What's the area of that? Well, it's 1 times 1, which is 1 centimeter squared. But I now want to do this in millimeters. So how many millimeters are there in a centimeter? There are 10 millimeters. So I've times that by 10. What about this one? 1 centimeter is also 10 millimeters. What have I done? I've times that by 10. So in the same way this time, I've got 10 times bigger that way and 10 times bigger that way, which means that I would have to multiply that by 10 and multiply it by 10 again. And again, we can write that in a simpler way as times 10 squared, which would actually give me 100 millimeters squared. So does that, is that what happens in this diagram? Centimeter squared to millimeter squared, oh my goodness, times by 10 squared. Ooh, this stuff is amazing. Now, obviously what we do, one direction, when we multiply that way, we divide the other way, but it's the same idea, okay? It's exactly the same idea. So we're now going to use that information to help us get here from millimeter squared to centimeter squared. Okay, so we've got 859 centimeters squared that I want to go to millimeter squared. Now, how do I do this? How many millimeters are there in a centimeter? 10. I'm doing area, so actually I'm going to do 859 times 10 squared. That's going to take me from centimeter squared to millimeter squared. Well, I know that that's 859 times 10 times 10, which is 859 times 100, which gives me 85,900 millimeters squared. Ka-ching. Now again, I didn't use that little doohickey we had in the previous one just because, well, I can use this. I can use the idea that I can go from centimeters to millimeters. How many are there? And then square it. What about this next one? 237 meters squared to centimeters squared. Right, how do I go from meters to centimeters? I times by 100. There's 100 centimeters in a meter. Yep, I'm doing area, so I square it, which gives me 237 times 100 times 100, which gives me 237,000. And then we are going to write centimeters squared there, and ka-ching, 2.37 million square centimeters. That's a lot. Wish I had that main money. Yes, never going to happen. Never going to be rich, never going to be famous. And so we go to areas of basic shapes, which most of you will know, lots of them already, and that's fine, not a problem, okay? How do we find the area of a basic square? Well, we know that it's that times that. For all quadrilaterals, it's length times width, or length times height, or you see, I don't even think of it that way. Whenever I teach this, I say, look for a right angle and multiply the two things together that it joins, because otherwise they throw in some interesting tricks for you. In this situation, we know that this length here is L. We know that length there is L as well, and I don't know why we use the letter L. It looks too much like a 1. Please stop using the letter L. But we now know that the area of this shape is equal to L times L, which we can write as L squared, because anything with a floaty 2 means multiply by itself. This one, we know that this length and this length are the same, that length and that length are the same, but the same point of it is, I can see a right angle in my quadrilateral. I know that it's that times that, which is length times width. Is that a width or is it a height? Too many people want to know. So area in this situation is length times width. Now I can't write that as L squared or W squared because I can only square when the letters are the same. Triangle, base times height and halve it. I use this all the time, but again, when I teach this, I look at where the right angle sign is, and that tells me which one's the base, which one's the height, and I just realized for a triangle that the area of this is a half times b times h, right? So base times height. Again, I don't like the letters. I use it by, well, hand actions really. What are the shapes? Well, these are the easy ones. Let's do some examples. Find the area of the following. Well, we know the area of that one is base times height, or just look for the right angle and the two sides. So that becomes 3 times 7, which gives me 21 meters. Correct? No, not correct, because we've got to have the floaty 2. Yes, remember the floaty 2 to show that we're working out an area. What shape do we have here? Triangle, mais oui. So we know the area here is a half times base times height. Which one's the base? Which one's the height? It's too confusing. Look for the right angle. There's the right angle. It connects that line and that line together. So it's a half times 5 times 11, which is a half of 55. And what is a half of 55? It is 27.5 kilometers squared. When I took this to my year 9s, there was some debate over this, but thankfully we got to 27.5. Now, this shape here is a parallelogram, which is basically a knocked over rectangle. And the area of this shape is, funny enough, base times height again. Love that rectangle, or the right angle, tells me which two sides to multiply together. Oh, hold on a moment. The right angle's down here. I don't know this length, Danger, Will Robinson. Actually, I do know the length because it's the same as this one here. Yes, because it's a parallelogram. So the area is 1.5 times 3, and again, you should be able to do this in your head, to be 4.5 centimeters and squared. Basic recap. More complex shapes. Oh, look, I put this, all right, I put it in now. I wanted to talk about it, but again, we know the area of this shape is base times height. What about a trapezium? I nearly called it parallelogram. What about a trapezium? Well, trapeziums, again, love it. Watch. Add together the parallels, multiply by how far apart the parallels are, and halve it. Add the parallels, multiply by how far apart they are, and halve it. So if I was going to write that in a formula, we would do A plus B, all right, because these are my parallels. How do we know that they're parallel? Well, these double arrows here show it to us. I'm going to times that by how far apart they are. Not easy for you to say. All right, and there we go. That's the right angle that tells me height, and then I halve it. And so that's normally the type of formula you'll see. Half in brackets A plus B times H. There's also another way of doing it. Sometimes I see A plus B in brackets times H all on 2. Exactly the same thing. But again, I don't think of it that way. Add times halve. And here is another funky example. Have we seen this shape before? Well, actually, the formula is on the next sheet. But I wanted to say to you, this here is a rhombus. Yes? How do you know it's a rhombus? Because all the sides are the same length, those little thing there, but they haven't given us that information, because to find the area of a rhombus, or in fact a kite, we need to know their diagonals. And a diagonal is a line that joins opposite corners together. So you'll notice that this red line here is a diagonal, and that line there is a diagonal as well, which means we can use a formula, and the formula is a half xy. Now, where on earth did they get this xy from? Well, basically, x and y are the lengths of the two diagonals. So in this situation, that would be a half times one of the diagonals is 10, and one of the diagonals is 9. Now, again, breaking this up, I tend to do a half times 10 is 5 times 9, and I know that 9 5s are 45, and don't forget my units of measurement, meters and millimeters squared. Okay, so a half times the diagonals times together. Here we go. Here's a practice. Do you remember the formula? Add, multiply, halve. So my area here is a half times, add together the parallels. Which ones are the parallels? They're the ones with the arrows. So that's 4 plus 6, and I'm going to times it by how far apart they are. How do I know that? Because of the right angle, times by 3. Now we know from bid maths that we have to do the brackets first. So that becomes a half times 4 plus 6 is 10 times 3. I know that a half of 10 is 5 times 3. And so 5 times 3 is 15. And don't forget my units with the floaty 2. More complex shapes. Yes, here we go. So we already know the area of this one here is a half xy. And actually, this shape here is a kite. So kite shapes also are interested in the distance between their diagonals. Now I know that sounds a bit weird, but here is the two corners opposite each other, and there are two corners opposite each other. And so the area, once again, is a half xy. Now you have to remember this stuff because it actually comes up much later in A-level and VCE here in Australia. It's a pretty funky shape. All right, so finally, more complex shapes. We're going to recap stuff we've already done previously. If you remember, the area of a circle is pi r squared. So pi times radius times radius. And I'll write that again. Pi times radius times radius. If I want to find the area of a sector, yes, and again, remember a sector is just a fraction of a circle. In this situation, we know that the fraction of the circle is theta divided by 360. So there's a fraction of, which is times, the area of that whole circle, which is pi r squared. And if you get that in your heads and remember that, put it in your summary book, you are going to ace this. Finding the area of circles and sectors. So find the area correct to 2 decimal places, which means it doesn't want it as an exact value. So we can now say that the area is equal to pi r squared. That's pi times my radius is 5.1 squared. Can I work that out in my head? Nope. So I'm going to fire up my calculator and I'm going to do pi times 5.1 squared, which gives me 81.71 centimeters and squared. Now, why are we doing it to 2 decimal places? because the question told you to. Let's move this over for a moment, and let's say we are now going to find the area of this sector, and that's going to give me the angle of the sector. So 260 out of 360, that's the fraction I've got of my whole circle, which is pi times my radius squared. My radius is given by 4. Yep, this is my radius. And now it's just a case of putting it into my calculator. I forgot what this was called then. 360. And we're going to multiply that to pi and multiply that by 4 squared, which I know is 16, but let's put it in anyway. And gives me 36.30. Must have that. And what units did they give me? Meters. Marvelous. Meters and squared. Once we know how to do this stuff, the questions are all fairly the same. And ladies and gentlemen, I am done. It is very good to see you. Thank you very much for watching. Hopefully you've enjoyed the video. If you can, subscribe to my YouTube channel, would be greatly appreciated. Again, it just lets me know that people are watching. I'm never going to be rich. I'm certainly never going to be famous. But just knowing you watch makes all the difference. Leave a comment if you can. Shout out to all your friends. Just let them know that I'm trying to make maths easy and understandable for you. I'm going to head off to do another video now. So hopefully I'll see you in that one. You take care of yourself. Stay safe. I'll see you soon. Bye.